Okay, good morning everyone. So my name is Philippe Caïs, I'm research engineer. I work at the Laboratoire Astrophysique de Bordeaux. It's one of the 1,000 labs working in a research in France. And I work for the French agency of research, which is called the CNRS. And I was part of and I'm very pleased to present you the development of the instrument that we call Supercam. Supercam is aboard the Perseverance instrument, and you will see it will be a technical presentation, a lot of picture, and I'm not sure you will learn a lot about the Mars planet, but you will, I hope that you will learn a bit about how complex is it, or how we have to deal with things to build an instrument to go in this harsh condition, because Mars is a bit harsh. Okay, so my agenda is Supercam is an instrument, but it's not from scratch. We have an heritage from the ChemCam instrument aboard the Curiosity rover. So I will talk a bit about the Curiosity and what discovered thanks to ChemCam. After I will show you a lot of a slide about the instrument itself and the team. It's a real collaboration between the countries, foreign countries, and also in France, because we are responsible for the development of the mass unit, the French part, and I was the project manager for that, and you will see the long collaboration for that. And after, as soon as we deliver to the Perseverance rover, I will show you what did the Perseverance rover, and after the next step, and I will introduce the next talk with Andrew, because I has a chance to work also on ExoMars program. Okay, so about the ChemCam, the ChemCam. ChemCam is an instrument built in the early 2000s and starting in 2004 for the Mars Science Laboratory that was called after Curiosity. And it's the first time that we use the laser induced breakdown spectroscopy. I will explain you a bit later what it means. But it means that we can analyze rocks at distance of few meters. That's very helpful if you have a rover moving everywhere. We can zap, we shoot on the rocks. We call that zapping, and we can zap on everything on the planet. So these two guys, it's Roger Vince from the Los Alamos National Laboratory, the LANL. And this guy is Sylvester Maurice from IRAP. They used to work together, postdoc and so on. And so it was the beginning of the US and France collaboration. It was delivered, so I work on this program also since 2006. And we delivered the instrument in 2010. And after that, we have to implement the instrument on the rover. They have to do a lot of tests, and they have to send the rover on Mars. It's on Mars still since 2012, so it's more than 10 years, and it's still alive. Curiosity is still alive, and our instrument is still alive and still firing on Mars after more than 4,000 sols. Sols, it's the day on the Mars planet. So ChemCam is very useful because thanks to this spectroscopy, it's a telescope, and we have a laser. We focus the laser on the small spot of 0.1 millimeter, and we raise the temperature of the rocks up to 10,000 degrees. So it's very high. It's a small spot, and the light coming back from this spot, we call that the plasma. The light coming back goes through the telescope also, and we have to analyze. And that was the ChemCam instrument, a laser and a spectrometers. And I will talk a lot about laser, spectrometer, and so on. So I try to be short. So after 10 years on Mars, what we have helped, it's the ChemCam instrument, because on the Mars Science Laboratory you have 10 instruments. It's 100 kilograms of science. We have other instrument from France. We have a very useful instrument inside the rover to analyze the chemistry. And what we have is that we find manganese oxide thanks to the ChemCam. So it means that the atmosphere in the past, billion years ago, was richer in oxygen. That's very useful to understand what was the condition of the planet billion years ago. And we also found borons, which is a key element for prebiotic element, and that's what we are looking for prebiotic and the beginning of life. And also we find some carbonates and sulfates, and we shoot on some salty, very small salt in the rocks, and that was very useful to help understanding the Gale crater geology and history for that. So that's all for ChemCam. Now we have the ChemCam successor, which is called, it's a super ChemCam. And so at the beginning, we start with a super ChemCam. We say, oh, it's like a Supercam, but we will find another name after. But if you find a name once, it's a finish. You cannot change at all. So it's a Supercam instrument, and we are using the same laser-induced breakdown spectroscopy that we call LIPS technique. We also implement Raman spectroscopy, visible and infrared spectroscopy. That was not at the time of ChemCam. And also that's the first time that we have a microphone, a scientific microphone on Mars that can listen to the rover, that can listen to the environment. And it's very useful for us to listen when we shoot on the rocks, we have the hardness of the rocks thanks to the sound coming back. So I also understand the ChemCam was 2 countries, US and France, and for the Supercam, we are three countries involved in that. The leader is the US at the Los Alamos laboratory, so it's a leader because it's a leader, let's say. Okay, but we have worked a lot, and France has spent a lot of people and money compared to US, but that's very, very useful to have a US instrument aboard a US rover. It's some kind of politics. Oh, sure, that video. Okay, so the US leader, they built the spectrometer in the Los Alamos laboratory. We built what is on top of the rover. It's for it's optics, laser. We built in infrared, and what is also very useful, and it's a key technology. It's a key element. We have a calibration target because it's an instrument. It's a scientific instrument, and we want to check during all the mission, during years, that there is no drift of the parameters. There is nothing going bad. We have calibration targets, so we would just turn the head and we shoot on the calibration target here. I will show you the target. So it's real collaboration, the same guys, US plus another guy, that was the guy was working with us on ExoMars program. So the body unit is let's say the main goal is to get spectra. So we need spectrometer, and Los Alamos is working on spectrometer. We have 3 spectrometer inside this box. So it's a small box. You can see it's a few kilograms, and we cover for 0.2 micron to infrared in 3 separate spectrometer. Each one is used for different things. The first for the LIPS, the other one for Raman, and the other one for IR spectroscopy, passive spectroscopy. And it's embedded in the body of the rover. So you can see the inside the rover at the GPL when they integrate all the things, all this cable, all this instrument, and the body unit is here. It's connected to the mass unit using a long fiber. They connected with cables, for sure, because we discussed together body unit and mass unit. And that we call the mass unit. It's a French contribution of the Supercam instrument. And as you can see, it's because it's outside the rover, the body of the rover. We have to cover. We have to cover the instrument because on Mars during night it's very cold. It's minus 120 degrees Celsius. So it's very, very cold. So we have a remote warming window, our box, electronic box, and we have some heaters during the night that can ensure that we are not below minus 40 degrees C, which is for instrument it's low. If you take your computer and you go to the ski station, you try to switch on when you are at ski station. It doesn't work. We did the experience with Michel here. So the normal electronics is not designed to work at this low temperature. We have to do that, and also we have to do it at high temperature. So it's a lot of tough. It's a tough. So you can see the Supercam is inside this box. And also you have the mass cam and you have the nav cam, and the fiber optics is rolled here because we have to move the mast to shoot everything on Mars. So it's a relaxation that we have here for the fiber. So data box, it's like a cabin baggage, so you can take it in a plane, so it works. We already did that. You don't have to say, but we already did that sometime. Not the flight model, sure, but the other model. And it's about 6 kilograms, and the energy is really important. We are less than 30 watt. You have to know that the rover itself has no solar panel, so it has about 100 watt of energy available for the instrument. So when the Supercam is working with the mass unit and the body unit, we are at half of the power. So it's a real constraint. And moreover, when we are during winter season on Mars, we have restriction for the use of the instrument. So it's operation constraint. And the third part of the instrument is the calibration target built in Spain, and it's at the rear of the rover that you've seen. We have 29 targets, which are rocks powder and different rocks for the calibration of the LIPS Raman and infrared. Also, we have a titanium plate. Titanium is well known for LIPS analysis. We know. We shoot all the time here to check that the spectrometer is working perfectly and the laser is working fine. And we also have a USAF pattern to calibrate the imager, because on our instrument it's a telescope, so we have an imager, very, very high precision imager, because for instance, on Curiosity, we were the best resolution camera on the rover. Now the mass cam is a bit better than us, but we are we can focus at 7 meters, and we have a very small field of view. So high accuracy. It's really important because I will show you when we shoot on the laser, we want to know where we shoot, and the spot is less than 1 meter. 1 millimeter, and we shoot at 10 meters. So high resolution spectrometer, and we can calibrate using this target. We also have a meteorite, so it's a small part of meteorite. That's a story. It's a meteorite coming from Mars, found somewhere on Earth. We bought this meteorite, and we sent back to Mars. So we already did the Mars sample return. It's done. Check. So if you are keen or if you are a fan of science, you can go to Toulouse and the Cité de l'Espace. It's a very, very exciting place to go. And they have the other part of the meteorite that you can see. Okay, down. Okay, I show you I have a movie on Supercam who explain better than me how it works. Oops.
3.5 billion years ago, before its atmosphere disappeared, Mars was partially covered with liquid water. Does it mean life could have existed on the red planet? NASA's new rover Perseverance is the best chance for planetary scientists to answer this question. It has landed in Jezero Crater, a former lake that offers great geological diversity and which may have preserved signs of past life. Its main mission is to collect samples that will hopefully be brought back to Earth in 2031 in order to undergo thorough analysis. For this purpose, Perseverance carries 7 instruments, including Supercam, as well as a drone and a system that allows it to core and cache the collected samples. Co-developed in France, the United States, and Spain, Supercam consists of 3 modules. The mast unit, the eye of Perseverance, for remote observation and infrared spectral analysis. The body unit to perform spectral analyses of the UV and visible light collected by the mast unit and communicate with the rover. The calibration targets at the back of the rover serve as a reference to validate the measurements taken. Supercam runs 3 complementary techniques of spectroscopy that use the same telescope and detectors. The LIBS spectroscopy uses the infrared laser to vaporize a few micrograms of the targeted rocks and generate a spark called plasma. The analysis of the light spectrum emitted by this plasma gives the chemical composition of each target. The Raman spectroscopy collimates a green laser. The targets are excited by this laser and produce photons whose wavelengths characterize their mineralogy. Finally, the infrared spectroscopy studies the sunlight which is reflected by the rocks. Variations in signal intensity determine the mineralogical signature of the target. Another important feature of Supercam is its very high-definition color camera. Thanks to its images, it will be possible to characterize the geological context of rocks and soil, which are analyzed by spectroscopy. Finally, the scientific microphone on board Supercam will capture the sounds produced by the impact of the laser in LIBS mode, so as to analyze the hardness and mechanical properties of rocks. It will also study the sound of the wind and give indications on the planet's meteorology. Supercam thus combines 5 measurement techniques into a single instrument, a true technological feat that makes it possible to characterize the geological and chemical environment of the samples that will be returned to Earth, and perhaps to answer in situ this fascinating question: was there ever life on Mars?
So, how can we do? How do we have to do to build such instrument? That's the point. The key response is collaboration. We work, as you know, we work with the US, we work with the Spain, and also in France we are 7 laboratories working. 7 laboratories from the CNRS, from the CNES, our French agency. And we were more than 100 people involved in that. And also we have industrial partner, and it's very, very important to have people you have to deal with this kind of people, and it's very important to have confidence between us. And at the end, there were more than 100 people working on that also. So under CNES supervision, and now that we have delivered the instrument, it's not finished. You know, you can see the building, the instrument building laboratory. It's 2 labs in Paris, 1 lab in Bordeaux, and the labs in Toulouse. And now we have more than 50 scientists working on the Supercam analysis and operation. And daily we have 5 people operating the instrument all the nights, because we work at the US time, all the nights with 5 people working to operate the instrument. Only our instrument. The rover itself, it's let's say 50 people working on that. So that was the beginning in 2015. It was the beginning of the story and the development. We were about 50 people in this meeting. It was in our observatory, in my lab, home lab. And after 50 at the beginning, 100 at the end, it means complexity and it means also dynamics. We have many people coming and to work with us. That was very exciting. So, an instrument is a lot of hardware, a piece of hardware, more than 200 parts that we design in our lab, and we go to partner, to industrial partner, to machine and to build. Or in our lab, we also do a lot of things. It's also many optics because it's a Schmidt-Cassegrain telescope. The primary mirror is about 11 centimeter. It's enough to have the resolution. Everything was computed by an optician, by an optical guy in Toulouse, and it's a lot of optics provided in France and in Japan also. So the key element in the instrument is the laser. The laser is done by Thales. Thales, it's an industry, French industry for that. And the key element is the laser. It's about the same laser as the ChemCam, so we have heritage on that, with a legacy. But we also implement another path of the laser. So the laser is at 1,000 micron, nanometer, 1 micron, and we have a frequency doubler. So we have a red laser and we have a frequency doubler to have the green laser. The red laser is used for LIPS because it burns the rocks. The green laser, it's a lower energy and it just make vibrating the molecule, and that's enough for Raman spectroscopy. I don't want to much into detail. If you have question, I can answer for that. So that's the laser, and we designed the laser board. The laser board to have this laser, it's more than 200 amps, so it's a lot of energy, but not only during 5 nanoseconds. So in total, we have a laser of about 10 megawatt, but it's very short. But we have to burn the rocks at 10,000 Kelvin, so it's a lot. And also we have to synchronize the laser and the spectrometer with the fiber. The center part of the instrument is also the computer, and we have this digital processor unit. There is a small component here, and it's based on FPGA and software core that we can program in C, not only in VHDL. And that's the core. That's the heart of the instrument. We interpret command from the rover, and we do all the science on that, and we synchronize everything. That was the key point: synchronizing the laser and the spectrometer. After we put everything in this box that we call the E box, and at the end it's more than 400 parts reference that we have to buy, so it's a bit expensive, and more than 3,000 parts to solder on the board. Only on the laser board to have more than 200 amps, we have 300 capacitor on the board. So it was a lot of work. After that, we have designed the board, manufactured the mechanical parts. We have to assemble in a clean room. As you can see, it's a clean room. I will come back on that. I can show you I can show you some picture or movie on that. We integrate the laser in a black coating tent, because the laser is dangerous for the eyes. So these people have to wear goggles also on top of all the equipment that we have, gloves and gear and so on. And it was very challenging to keep the cleanliness of the instrument. And that's what we do. We shot on the laser. You can see the shot on the laser. It's very small, but it's enough to get the spectra. After that, when we build the instrument, we have to test to check that it can survive to the vibration of during the launch in the rocket. Also, when you arrive on Mars, we have a shock. We are just pushed deposit on Mars, and it's a lot of vibration and shock. So we have to test that. We also have to test the GPL. So they have some kind of mock-up, and we do shock on that. I could show you. And also we have to test if it survives or if it's working at low temperature. As I said, our instrument is working at minus 40 degrees C, but we have to, during the day, it's warming up with the sun, and we can go high to 50 degrees C inside the box. So we have a difference of 100 degrees C, which is very painful for the optics alignment. That was a big deal. So what were the challenge? The challenge to do Supercam compared to ChemCam. In the same volume and in the same mass, because we were on top of the rover, and the Perseverance rover is about the same as the Curiosity rover. We have to put more techniques, more things in the same mass and volume. So that was very tough at the beginning. It was very constraining for us, and especially for the mechanical guy. What we have to check also if it's optics quality, the image quality. In fact, during some tests on some model, I will show you different different prototypes that we built before the flight model. We had the RMI image degraded at low temperature. So it was working fine at room temperature, but when we go down in temperature, it was a bit nasty. So it was the disalignment of the mirror and everything. And at the end, we discovered very late, just before the flight model manufacture. So it was just on time, let's say, but very late. We discovered that it was just a matter of coating of the primary mirror, and we have to change the coating, and we have to change the procedure at the manufacturer. So it was also a big deal for the manufacturer to change the things. But it worked at the end, and they spent many times to have this new technology. And one of the most challenging issue was on ChemCam. We used to have only one telescope and one laser going through the telescope. So the laser is shooting here. There is a mirror going here. When you shoot through the telescope, the plasma, the light of the plasma is going back, and it's the same telescope, so it's fine. So if you move the telescope, you have the position is exactly the same. You look where you shoot, so that's okay. But that was for LIPS. For the Raman techniques, we have to. It's not the same laser path, because it's not the same laser. It cannot go through the telescope, because otherwise it burns the rocks. And we don't want to burn the rocks with the green laser. We just want to do excitation of the molecules. So it's low energy. So we have to separate the path. And you have a small Galileans here, a small tubes here. And after, it's going here. And we go in the same direction. The problem is when this plate is rotating. And it's rotating in temperature. And we spent hours, weeks, and more to check and to find a solution, not that the laser is aligned with the green laser is aligned with the red laser. And we have many test weeks and in thermal chamber to check. At the end, we discussed with the CNRS and with the GPL guys, and we found a solution. And at the and finally, we recommend to the GPL to open our instrument at low temperature when it was cold on Mars, because it was some kind of hysteresis. When you go down and up in temperature, the laser was not moving the same position. So it works, and on Mars now we have a very good precision and very good accuracy on the pointing of the laser, and it's very useful because even when you do green laser, you have to collect with the same telescope. And one of the challenging was the planetary protection. If you remember on Curiosity in 2015 and 2016. They find some bright, it means some salt and water, and close to the rover, not too far away. But the Curiosity rover has not the authorization to go there because it was not clean enough. It should have been very interesting. It could be very interesting to go there with Curiosity, because Curiosity has a laboratory inside, which is not Perseverance is not that. So for Perseverance, if we want to find the microbiologic samples and not to make pollution on that, we have to be very clean on our instrument. So we have all these habits, or of the gloves and so on, and we make several swabs and so on. At the end, when we arrive at GPL and we deliver the instrument, the first thing they did is to put our instrument in the oven, in a thermal chamber, and to check if we release the things. They just heat up a bit, and we release the things. And the results were good, so we were authorized to go to the rover. And we spent many times to clean with alcohol and so on. We could not put at high temperature because of the optics, so we have to be very clean at the beginning and during the process. As you can see, it's because we are in the seal, we are in the airweb window. We have 1,000 spores per square meter, but the microphone is outside, so the microphone needs to be cleaner. And that's why we have alcohol everywhere to clean to do that. Okay, to do the instrument and to do the flight model, the one on Mars, we have to build several instruments. The first one is the prototypes, and it was also scheduled to build 3 instruments in 3 years. We start in 2015, and we have to deliver 2018. And for us, it's very challenging. 1 instrument per year, it's crazy. So we first with an engineering model, we start in 2015, and because we have to build it very quickly, we use even spare parts from ChemCam, spare optics. It was the first instrument that was demonstrating that we can do Raman, ellipse, and VSIR, and color imager. Very useful, this model, and we deliver after we test in France. We deliver to Lanel, and during 2 years they use for the spectrometer. And at the end, we have to deliver to GPL because they want to test 1 instrument. So we remove the laser, we remove things because it was not useful at GPL. Only the camera and the telescope, and they put on their test bed. They have rover test bed. And to make to help programmers and the software guys for the closed loop pointing and autonomous pointing of the targets, and it was very useful for that. After we built what we call the structural and thermal model, it's only mechanical things. There is no electronics inside, and the goal is to to make shock on that, to make vibration, to be sure that the structure can survive the vibration and so on, and the thermal. And at the end, because we had this issue on the rotation of this plate, we went to CNRS and we put some painting, and with stereoscopic cameras inside thermal chamber, we look at how the Schmidt plate was rotating during the thermal cycling. And we discovered that there was an hysteresis. It means it doesn't come back at the same position when you go to low to high and high to low. It's crazy. But several weeks, and this one, we shoot on this instrument more than 100 times. A lot of shock. Okay, and after in 2017, we built the qualification model. The qualification model is the flight model, except that we don't have the space grade component because it's very expensive component, so we don't have that. Otherwise, the rest, the other things are exactly the same, the optics, the mechanic, and so on. And on this model, you pass everything at high level, vibration and so on, high level. More than the flight model, because the flight model will also have the vibration during the shuttle. You don't want to make fatigue on that. So you need this kind of instrument. And at the end, end of 2017, after the fabrication of the EQM and the test of the EQM, we go to flight model, which is a copy of the QM. And it takes around 1 year to build the model, and we assemble the model, and we go to vibration, we go to thermal chamber, to thermal vacuum. And in October, just before 1 month before the delivery, we had an issue. Houston, we have a problem. We put this instrument in a thermal chamber to accelerate the gluing of some cables, the last spotting of the before delivery, and the thermal chamber malfunction, dysfunction, and raised the temperature up to 2050 degrees C compared to 50 degrees C. So we have to remove the instrument and to scrap everything. So we had long discussion with our French agency, with GPL, with Los Alamos, and also with our industrial partner, and we decided to rebuild an instrument, and we did that in 6 months, which is very, very challenging. But the people have to work 24/24. We have to work during the weekend and so on. And that's why we increased the team. The team was increased by a factor of 3 to build the instrument in 6 months. But everybody played the game, and we did it. And that finally it's working. Yeah, that was a good adventure. Not the accident, not too good. So at the end, we deliver in June 2019. So it was a bit 6 months late compared to original schedule, but we could. Was not too late to go to the rover, of course. And that's the photo, the picture of the team during the delivery. The instrument is inside. And during July, they put the instrument a few days after, they put the instrument on top of the rover here. And we have our guy looking for the instrument carefully. And that's it. During a few months, they test on the rover, and after they deliver to Florida and to Kennedy Space Center, and in July 2020, it started, it launched, and go to Mars, arrived to Mars in 21. So, good story, a happy end story, I would say. It was not always the case, but we were very happy. So on the Perseverance rover, I checked the time. On the Perseverance rover, what is the mission of the rover itself? To do geology exploration, to understand where we are on the G0 crater, habitability and biosignature. That's really important to prepare the sample, the cache, because most of the science mass is taken by the sampling, the cache sampling instrument, and also prepare for human exploration. So you have the MOXIE that fabricate oxygen in situ. And you have several instruments. One in Spain, it's a weather station, cameras, and you have the first ground-penetrating radar inside the surface. That was very RIMFAX. It was a collaboration with the ExoMars, the same guys at ExoMars. And also we have two very good instruments, Sherlock and Pixel, that are on the arm and on contact, analysis in contact. We shoot on the laser, we shoot on the rocks everywhere, and when we have something that we say, okay, stop, go there, the arm, do the science in contact, and after we do the sampling. So Supercam is very useful because we don't have to move the rover. In fact, we have the image of the rover at night. We have the image of the rover. Where is the rover? We have image everywhere, and we decide to shoot on the rocks and everything moving on Mars. So we shoot on that. So and we say after, okay, go, stop, and do some science contact analysis. We can do that with our techniques. It's because we are on top of the Mars, we have good images, and we can do geology, understand geology, and because we have a microphone, we have metallurgical also and atmosphere understanding. So after more than 600 souls, 1,000, we have shot more than 600,000 shots, so it's a lot. Yeah, I'm finished. On more than 1,000 rocks, a lot of images, a lot of sounds record, more than 30 hours of records. We discovered that we can hear the drone Ingenuity far away. It was not expected. So we discovered also that sound on Mars is weird, not the same speed of the sound depending on the frequency. So it was not expected, and that's the first time that we have some electromagnetic discharge in the dust deville that we have recorded. That's the first time that we can see activity on another planet. The geology, what the outcome? It's a Jezero crater, it's a lake, it's an ancient lake, more than 3 billion years. We have volcanic rocks on the bottom of the lake, but deposit in the delta, and a lot of variety on the rim. So it means that it's very complex to understand the history of the Jezero crater. But Supercam is very useful. We have past evidence of past stability. NASA published a paper on that in September, and say, okay, on Sapphire Canyon we have a sample that we need to get back on Earth. So okay, go for the sample return program. That's our message. And Ingenuity can fly on Mars. That was not expected that a small drone could fly on Mars. The next mission, like a dragonfly on another planet or satellite of planet, they will have drones also. That was a demonstrator. Very simple. At the end, after a lot of kilometers, we collect 30 samples. We have 8 tubes left. That's not there. We also have made a deposit of 10 samples. We have the copy of these 10 samples in the rover, but we already pushed 10 samples outside the rover. If the rover failed, we can have access to the tubes. You can have access to these 10. And we are ready for the sample return, and that's our message. Okay, that's the traverse of the rover. It's the Gale crater, the Jezero crater is here. We are on bottom of the lake. We go to the delta, and now we're on the rim, and we go outside the rim now for science. Okay, conclusion. I'm fine for the time. Supercam, as you understood, is one of the most complex instruments on another planet. A lot of techniques in the very small room for that. It's based on unique collaboration between countries, Spain, US, and France, but also inside France, a lot of laboratories, a lot of industries involved in that. It's extremely useful for the rover. We are on top, but also we have geologists. We have a specialist on geology, on Martian geology now. Our guy published the first paper on the Perseverance rover in Science. So we are real expert because these guys work for Mars for 20 years. Curiosity and Perseverance. It was a human experience marked by highs and lows, surprising turns, happy ending. We did it, and thank you. I want to thank the Supercam team. I'm just representing the team, and I was very proud to be managing this program. Thank you very much. I follow with Andrew's presentation on ExoMars rover. We have 8 instruments. We have six French contribution that we have built instrument for ExoMars, and also we have the Martian moon exploration. I just took the Martian, the MMX. We have 2 in contribution. One is an infrared spectrum. The same team, exactly the same team. Paris, Toulouse, Bordeaux, the same teams. And the CNRS manufactured the IDFX rover. It's a very small rover, and we're very nice to have this one. Thank you very much. I'm finished. Thank you.